Hello everybody, my name is Ricardo Pimentel from the Civil Construction Institute. In this presentation will be focused on the fire design of simply supported composite beams and slabs according to Eurocode 4. So the program includes a brief overview of the fire design of composite beams and slabs. We'll be looking at the influence of the slab temperature or concrete flange temperature on the fire resistance of composite beams and slabs. Comparison between Eurocode 4 methods and numerical methods to establish temperature profiles or critical temperatures, and later the fire protection of a composite beam. A simplified method to assess the critical temperature of a composite beam will be discussed, and we will be looking at the main conclusions of the article. While designing a floor plate, which includes the beams and the slab, one needs to fulfill two criteria: structural capacity of the members and also thermal insulation. So structural capacity, which is covered by the code 412, one needs to establish a temperature profile in the cross-section of our element. We need to account for reduced material properties at elevated temperature and complete the design against the fire loading. In terms of thermal insulation, one needs to respect a minimum slab thickness to control the temperature on the top surface of the slab. This thermal insulation is covered by EN 1363 Part 1, although Eurocode 412 also covers this in Annex D. There are several references which address the fire design of composite elements. So in addition to Eurocode 4, there is also the PS 5950 Part 8, or more recently the Australian New Zealand Code 2327. And targeting the UK market, there is the NCCI PN 005C, which provides temperature profiles in composite slabs, as well as the minimum slab thicknesses to fulfill the thermal insulation requirements. Giving a bit more detail about the thermal insulation criteria according to EN 1363 Part 1. So there are two requirements that need to be fulfilled by the slab. So a mean temperature rise on the top surface of the slab is required to be no more than 140 degrees, while the absolute maximum temperature rise, again on the top surface of the slab, is required to be no more than 180 degrees. So different fire ratings, they will require different minimum slab thicknesses so that these requirements are fulfilled. So considering these two requirements and assuming a room temperature of 20 degrees, it's likely that the top fibers of the slab will not be exposed to more than 200 degrees. And in fact, 200 degrees returns a reduction factor or for the concrete element of 0.95, which in fact suggests that the concrete resistance at elevated temperature of those top fibers of the slab are close to the room temperature resistance. So therefore, little reduction is expected for those fibers or the top fibers of the slab. In addition, the material partial factor for fire design for the concrete element is equal to 1. Considering a composite beam as example, typically the steel element has a critical temperature around, say, 600 to 700 degrees, which means that the strength reduction factor for fire design for the steel is likely to be between 0.2 to 0.4. On the other hand, as we discussed in the previous slide, the top fibers of the slab have plenty of resistance ensured by the thermal insulation criteria, and also considering that the material partial factor for fire design for the concrete is equal to 1. So it's clear that a very modest depth of concrete is likely to be required to balance the steel resistance and obtain the plastic bending resistance of our cross-section for fire design. So the question here is, and that we would like to answer with this article, is if there is a big error in simply assuming that the concrete flange temperature is the room temperature, which simplifies the design procedures and design rules for these elements for the sagging bending resistance of beams and slabs. To evaluate the influence of the concrete flange temperature in the fire resistance of a simply supported composite beam, three different models were considered. So detailed temperature distribution according to Eurocode 412 Annex D, which is the benchmark case, and two simplified approaches, so room temperature, or assuming that the concrete flange temperature is equal to 40% of the steel beam top flange, which is a rule used to calculate the concrete resistance or the concrete mode of failure of a shear stud in fire. So for these three options, several design cases were considered, more than 3,000 cases, which considered S355, C2025 as concrete grade, 90 minutes of fire exposure, 2 different critical temperatures, 2 different slab thicknesses, which cover the typical slabs in the market, 3 different degrees of shear connection, and 138 standard steel profiles. On the left, we have the comparison between NXT and room temperature. So the differences are small between the two approaches. The maximum difference is roughly 3%, although unconservative. On the right, we have the comparison between NXT and the 40% rule. These two approaches, they really match each other. So the differences are very small and conservative, but the differences are less than 1%. So both approaches, they give sensible results with minimal differences in comparison with the detailed approach, and they may be therefore used to simplify the design rules in practice to design composite beams or composite slabs in fire. So I also include composite slabs in this conclusion because for slabs the amount of steel that needs to be balanced by the concrete is much less. So we will have the rebars in the rib and not a steel profile. So the depth of concrete that will be required to balance the steel resistance is much smaller. So the second topic that I'd like to discuss establish a comparison between the Eurocode 4 rules and numerical methods to evaluate temperature profiles, critical temperatures, and fire protection of composite beams. To complete those comparisons, a beam was designed for room temperature, as shown here, so a 12-meter beam, which will be used for the comparisons that we will show in next slides. For the examples shown in the previous slide, 3 different approaches to assess the beam critical temperature were considered. So the first approach was to assume a temperature profile considering the Eurocode 412 rules. So based on plate section factors for the bottom flange, web, and top flange, a temperature profile is therefore established. Uniform temperature distribution for the whole cross section, and the so-called engineered method, where the designer specifies different temperatures for the web and flanges. And the objective of this approach is to allow for a higher temperature in the web, because the web is in fact responsible for more than 50% of the area to be protected, and it doesn't really contribute much to the critical mode of failure, which is bending. Of course, that this approach will require different projection thicknesses for the web and flanges, but it's something that is perfectly possible to do in practice. Although the 3 approaches, they consider different temperature profiles for the steel element, they do provide a very similar plastic bending resistance, as can be seen in the top table on the right. So a generic protection system was considered, which was also later used for the numerical studies. And for each one of the approaches, the protection system volume was calculated, and it was concluded that the so-called engineering approach could allow for savings in the protection system volume up to 10 to 15%, which is attractive for practice. For the 3 options discussed in the previous slide to assess the composite beam critical temperature, numerical studies were completed with the objective of comparing the temperature profiles between the analytical and numerical approaches. For the first approach, where a temperature profile according to Eurocode 412 was considered, it was concluded that the bottom flange temperature follows closely the web temperature, so some differences in the temperature profiles were found. The second option was to consider a uniform temperature distribution, and both analytical and numerical approaches they show very similar results. So the third option was to consider an engineered temperature profile allowed by different protection thicknesses for the flanges and web. And the differences between the analytical and numerical approach in the temperature profile are up to 5 to 6%. So namely the bottom flange is a bit hotter in the numerical simulation, which can be attributed to the fact that there's some heat transfer between the plates, between the flanges and web, although those differences in the temperature profile, they represent a difference in the bending resistance of roughly 5%. So on the left, we have a summary of the comparison between the analytical and numerical approaches, and it was concluded that the differences in the temperature profiles is no more than 5 to 6%, so the three options provide very similar answers. On the right, we have a further study which compares the effective depth proposed by Eurocode 412 to assess the slab minimum insulation thickness. So a numerical simulation was completed to evaluate if the temperatures imposed by EN 1363 Part 1 to fulfill the thermal insulation requirements are fulfilled with such equivalent depth, and it was concluded that the maximum temperature rise criteria may not be fulfilled while considering the minimum effective thickness given by Eurocode 412 Annex T. For this reason, there are other documents that suggest a different approach, perhaps more derived for specific products, specific decks, specific composite slabs, as we have in UK with the NCCI. Because simply supported composite beams are not susceptible to buckling, there is an opportunity to derive a simplified formula to assess the composite beam critical temperature. There are some references that refer that the rules from Eurocode 312 may be used, so there are some simplified rules for steel elements, although those rules tend to be conservative for composite beams. So a new formula was derived for composite beams, shows on the top left, which provides less conservative results in comparison with the equation for steel elements, although still conservative in comparison with a more detailed analysis. So as main conclusions, I would like to highlight that it was proven that the temperature profile in the concrete flange has a minimal impact in the bending resistance of composite beams and slabs, as long as the minimum insulation thicknesses are respected. So assuming room temperature for the concrete flange provides a good approximation for the bending resistance of composite beams and slabs. Specifying different protection thicknesses for the flanges and web may lead to a reduction of the protection system costs. The transfer between cross-section parts, so web and flanges, has impact on the cross-section temperature distribution, although leading to small differences on the bending resistance at elevated temperature. The effective slab thickness, according to Eurocode 412 Annex T, fairly addresses the mean temperature rise criteria for thermal insulation for composite slabs, but the maximum temperature rise criteria may be underestimated. A simplified method to assess the critical temperature of a composite beam was proposed, which provides a sensible but still conservative result in comparison with a more detailed analysis. Thank you very much.